Hello viewers, in today's lecture we are going to study about some special integrals. These special integrals will be applied for solving some integration problems. So let us first derive these integrals. Clear? So the first one is integral of 1 over x square minus a square. Okay, suppose we have an integral of this form, then we have the direct formula for solving such integrals as 1 over 2a log of x minus a divided by x plus a plus c. Clear? Now here's the second one is, suppose we have to integrate a function 1 over a square minus x square. Then the formula for such an integral is 1 over 2a log a plus x divided by a minus x plus c. Clear? Now the third one is, if we have an integral of the form 1 over a square plus x square or x square plus a square, then we have this integral equal to 1 over a multiplied tan inverse of x over a plus c. Clear? The fourth one is, if we have an integral 1 over square root of x square minus a square, then it is equal to log of x plus square root of x square minus a square plus c. Clear? Now the fifth integral is, suppose we have to integrate 1 over square root of a square minus x square, then it is equal to sine inverse of x over a plus c. Okay? And the last one is, here we have the sixth integral as dx divided by, here we have x square plus a square is equal to log of x plus square root of x square plus a square plus c. So viewers, here we have these 6 special integrals, and these integrals will be directly applied for solving other integrals. Clear? Whenever we solve a problem on integration, we try to reduce the integral into one of these forms, and once we get one of these forms, then we can directly integrate that function. Clear? So here I have listed out these 6 important integrals. Now I am going to derive these results one by one, but before deriving I would like to tell you one thing. Here we have dx over x square minus a square. So whereas this can be also written as 1 over x square minus a square and dx. Clear? So here integral dx over x square minus a square means we have to integrate 1 over x square minus a square. So the function is of this form. Clear? So our integrand is 1 over x square minus a square. Clear? And similar explanation goes for other integrals. So this is 1 over a square minus x square, this is 1 over x square plus a square, this is 1 over square root of x square minus a square. Similarly, this is 1 over square root of a square minus x square, and this is 1 over square root of x square plus a square. Okay, so if we write dx divided by x square minus a square, it means 1 over x square minus a square dx. Clear? Now the second thing I want to mention here, that suppose we have an integral, say x square minus 16. So where's the importance of these integrals is, suppose we have to integrate this function, so we can write it like x square minus 4 square dx. Now see, this integral is of this form, so we can directly apply the formula 1 over 2a log of x minus a over x plus a plus c to this function. Clear? And similarly we can write other integrals for these integrals. Clear? So let us derive these 6 important integrals one by one. Clear? Now viewers, let us take the first integral here. So let us suppose I is equal to integral of 1 over x square minus a square. Clear? Now here we'll first express this function that is 1 over x square minus a square as x minus a, this is x plus a. Clear? So here we have applied a square minus b square formula or the identity, and we have x minus a, x plus a. Clear? Now here we can express 1 over x minus a multiplied x plus a in terms of partial fractions. Now viewers, in my next lecture I will be dealing with this concept of partial fractions, but here I am telling you just the introduction of partial fractions. Clear? So here we have two linear factors, so we can write it as a divided by x minus a plus b divided by x plus a. Clear? So we have reduced this function 1 divided by x minus a x plus a into two fractions. Clear? So now we can write it as a times of x plus a plus b x minus a taking LCM, and we have x minus a x plus a. Clear? Now 1 over x minus a x plus a is equal to a times x plus a plus b times x minus a divided by x minus a x plus a. So therefore this 1 is equal to, the denominators are same, so 1 is equal to a times x plus a plus b x minus a. Clear? Now here we can write this expression as a plus b times x plus a minus b. Clear? Now if I compare both the sides, we see that the coefficient of x is a plus b here, and the coefficient of x here is 0. Clear? It is 0x. So a plus b is 0, and the coefficient of here the constant term is a times a minus b is equal to 1. Clear? So from here we have a equal to minus b, and if we substitute here we get a times a plus a equal to 1. So 2a times a is equal to 1, and we have a is equal to 1 over 2a. Clear? And similarly b is equal to minus 1 over 2a. Clear? So here's when we express this rational function, this is a rational function. So into partial fractions, when we split this rational function into partial fractions, we have two equations here in a and b, and we solve them and we get a is equal to 1 over 2 times the small a. Similarly b is equal to minus 1 over 2 times small a. Now we substitute these values a and b in equation 1. Clear? So therefore I becomes, this is the integral, and we have 1 over x square minus a square, because this can be written as 1 over x square minus a square times dx. So 1 over x square minus a square can be written like this. So a is 1 over 2a divided by x minus a. This is minus 1 over 2a divided by x plus a, and this is dx plus c. Clear? Okay, so here now we can write this expression as 1 over 2a. We take 1 over 2a common, and we have integral of dx divided by x minus a, and then we have minus integral dx over x plus a plus c. Clear? So this is 1 over 2a. Integral of 1 over x minus a is log of x minus a. This is minus log of, this is x plus a, so we have log of x plus a plus c, and we have 1 over 2a, and this is log of x minus a divided by x plus a plus c. So here's this is the required integral of 1 over x square minus a square. Clear? Now here's I am not deriving this formula number 2, and it is left for you as an exercise, because this can be derived similarly by following the process which we have used for deriving formula 1. So now let us come to the third integral. This is dx divided over x square plus a square, and suppose it is I. Now here we'll derive this formula by making use of substitution method. So here we will integrate this integral by using the method of substitution. So let us substitute x is equal to a tan theta here. Clear? So this expression x square plus a square becomes this is a square tan square theta plus a square, then we have a square common, then we have tan square theta plus 1, then we have a square times secant square theta. Okay, so this is the value of x square plus a square. Now from here we also have dx over d theta as a sec square theta. Clear? So here we can write dx is equal to a sec square theta d theta. Clear? Now substituting these values in this integral, we have I is equal to the value of dx is a sec square theta d theta, and the value of x square plus a square is a square sec square theta. Clear? Now here sec square theta get cancelled. Here we have a and 1 power is it gets cancelled. So we have d theta divided by a, which can be written as 1 over a and d theta. Clear? Now viewers, the integral of d theta is simply theta, and we have the constant of integration as plus c. Now we have to find the value of theta. From this expression we have tan theta is equal to x over a, so theta is tan inverse of x divided by a. So we substitute the value of theta here, so we have 1 over a tan inverse of x divided by a plus c. Clear? So this is the required formula for 1 over x square plus a square. Clear? Now viewers, let us come to the fourth integral. Here we have I is equal to integral dx divided by x square minus a square. Here also we will make use of substitution method, and here we will substitute x is equal to a. This is a sec theta. Clear? Here we will substitute x is equal to a sec theta. Now then this expression is square root of x square minus a square becomes this is a square sec square theta. We will substitute x equal to a sec theta here. Then we have here a square, then we take a square common, then we have sec square theta minus 1, and we have a square. We know that 1 plus tan square theta is equal to sec square theta. So sec square theta minus 1 is tan square theta. Then we have a tan theta. Clear? Now from here we have dx over d theta is equal to a sec theta tan theta, because the derivative of sec theta is sec theta tan theta. Clear? So where's dx is equal to a sec theta tan theta and d theta. Now let us substitute these values in this integral. So we have for dx we have a sec theta tan theta d theta divided by square root of x square plus a square is equal to a tan theta. So where's tan theta get cancelled, similarly a get cancelled, and we have integral of sec theta d theta plus c. Now the integral of sec theta is log of sec theta plus tan theta, and this is plus c. Now our aim is to express this theta in terms of x. So from here we see that the value of sec theta is x divided by a. So here we have x divided by a plus the value of tan theta can be written as sec square theta minus 1 plus c, and then we have log x divided by a plus the value of sec theta is x square divided by a square minus 1 plus c. Now this expression can be written as log of x divided by a plus square root of x square minus a square divided by a plus c, and viewers, this can be written as x plus square root of x square minus under root x square minus a square divided by a plus c, and by the property of log this can be written as x plus under root x square minus a square plus c minus log of a. Clear? Clear? Now this c minus log of a is some other constant, say c1, so this expression can be written as log of x plus under root x square minus a square plus c1. Clear? So this is the required integral of 1 over square root of x square minus a square. So here this c is actually c1. Clear? Because c1 can be or it is written for c minus log a. Log a is a constant, so c is constant, so c minus log a is another constant. Clear? And here we have applied the rule for the log, the properties of log, that is log m divided by n can be written as log of m minus log of n. Clear? Now here's the process for deriving integral 6 is same as integral 4, so I left this problem for you as an exercise. So let us derive this integral number 5. So we have I is equal to dx integral dx divided by a square minus square root of a square minus x square. So here's let us derive this by again using the substitution method here. Here we will substitute. The appropriate substitution is x equal to a sine theta. Then this expression square root of a square minus x square can be written as square root of a square minus this is a square sine square theta. Then we can take a square common, this is 1 minus sine square theta. Then we have a square times cos square theta, because 1 minus sine square theta is cos square theta, so we have a cos theta. Clear? And from this expression we have x over a is equal to sine theta, so theta is equal to sine inverse of x over a. And from this expression again we have dx is equal to a cos theta d theta. Clear? So let us substitute these values in this integral. We have I is equal to dx. For dx we have a cos theta d theta, and for square root of a square minus x square we have a cos theta. Clear? And a cos theta get cancelled. We are left with integral of d theta plus c, and this is theta plus c, because the integral of d theta is theta plus c, and theta can be written as sine inverse of x over a plus c. So this is how we derive this integral 5. Clear? So viewers, in our next lecture we will be solving some problems which are based on these integrals. Thank you.